The title of my talk is Actin Filaments Growing Against a Barrier with Fluctuating Shape. This work is done with Rajkumar Sadhu. He is a PhD student at SN Bose Center. Actins are cytoskeletal proteins which play an important role in cell motility. And these filaments have this special property that they can generate forces just using their polymerization and depolymerization dynamics without taking any help from molecular motors. When these actin filaments elongate, if they encounter a barrier in their path, then they generate a pushing force against that barrier. And this force is possible to measure in vitro by applying an external load on the barrier in the opposite direction. So you can, as you increase the load, the velocity of the barrier goes down and down. And finally, at some value of the load, the velocity is zero. That is called the stall force, and that is the measure of the maximum polymerization force generated by the filament. Because when you are applying that amount of force in the opposite direction, the motion of the barrier is stalled. Now, one important quantity to measure in this case is how the velocity decreases with force. And this force velocity characteristic is one very important component to understand the force generation mechanism. And so a lot of experiments and theoretical work focus on measuring this force velocity characteristic. However, it turns out that even the detailed qualitative shape of the curve, namely whether it is a convex curve or a concave curve, that depends on the details of the experimental setup. So some of the experiments measure a concave force velocity curve, some experiments measure a convex force velocity curve. For theory, to develop a theory of this process, the simple concept of Brownian ratchet was introduced for explaining force generation by a single actin filament. And in this work, what they had considered is there is one actin filament that is growing and one barrier is placed in front of it, and the barrier is having its own thermal fluctuation, and whenever there is a gap created between the filament tip and the barrier, one monomer would come and insert itself in that position. And this way the polymerization process goes on. And this mechanism predicts a convex shape of the force velocity curve. However, when this is generalized to multiple filaments, then it turns out that the shape of the curve again depends on several details of the model, like what is the interaction between the filament or how the applied load is being shared among the filaments. And in fact, Dibyendu, along with some of his colleagues at IIT Bombay, Ranjit, Mandar and few others, have recently done some very interesting works where they have probed some of these questions. Now, inside a cell, when actin filaments grow, they push against the plasma membrane. And this plasma membrane is not a rigid object, but it is elastically deformable. Even in vitro, when it's not a cell membrane, but some obstacle, but that obstacle can in general have some shape deformation. And this could be crucial because if the barrier is flexible, then it is possible that the filament can polymerize just by causing a local distortion. For this, they have to overcome just the local bending energy, which is much less compared to the case of a rigid barrier when they have to move the whole barrier in order to create some space for polymerization. So one might expect that this membrane elasticity might give rise to a larger velocity for a given load. So we propose a very simple lattice model for a barrier with shape fluctuation. We model the barrier just by a one-dimensional surface which is fluctuating, whose height is fluctuating. In presence of a load, we just model the local height fluctuation of the surface by a simple KPZ dynamics. And due to this dynamics, the surface tends to move in one direction, which is the direction opposite to that of polymerization. And the filaments are growing, so they push against the barrier, and there are two possibilities here. Either they can cause a local change in the surface height, or they can move the whole surface globally. And the question, of course, this local change requires much less energy, And when it is a global movement, it costs a much larger energy. And we are asking questions like how the barrier fluctuations affect the filament dynamics and how presence of the filaments affect the shape of the barrier. Note that in this case, since the barrier has a fluctuating shape, how the shape of the barrier gets affected in this process is also an important way to characterize the system. There is a load acting on the system from the opposite direction. That's why we are expecting the height fluctuations won't be symmetric. So this is the model. So we just model the actin filaments by rigid rods, which are made of monomers. And this is the barrier, which we model like it's a KPZ surface. And there is a force acting on it in this direction. So notice one thing, that if this filament has to polymerize, it has to push the whole surface up. On the other hand, if this filament has to polymerize, it can just flip this local valley to a hill, and that costs much less energy. In fact, energy cost in this case is L times smaller than this one. Apart from this, the surface can also have its own independent thermal fluctuations, and which again follow this KPZ dynamics. In general, because this load is acting in this direction, surface tends to move downwards, so which means hills are preferentially flipping to the valleys. However, if in this site, we call this a binding site, where a filament is present, this hill to valley movement may be blocked because the filament is in contact. L is the system, the number of sites in the surface. It's a lattice model for the KPZ surface, so it's just the number. It's a barrier size. L is in the unit of lattice sites. So essentially, so F by L, you can think of it, it's because when you have a barrier, one load is acting on it. So here, it's like F by L is the local, force acting per site. So first I present the results for single filament. So so the velocity of a barrier is defined as the rate of change of average height. And this is our result. The first note, right now look at the discrete points. So first result is the force velocity curve is convex. And not only that, for small or intermediate force value, the velocity actually decreases exponentially with force. And only at large value of the force, there is a deviation from this exponential dependence. This means that for small and intermediate force value, it's the global movement of the barrier which is controlling the motion, dominating the motion. And for large F, it's the local fluctuations which are pushing the barrier. And when the velocity becomes 0, that is the stall force. And here we show the plot of stall force as a function of barrier size. And we see that it increases with the barrier size. Now this result is somewhat counterintuitive because often stall force is interpreted as the maximum polymerization force generated by the filament. The fact that we are finding it depends on the size of the barrier is somewhat surprising. These continuous lines are from our analytical calculation. To calculate it analytically, first notice that there are two components of motion. One is the global movement. And to calculate the velocity due to global movement, what you need to know is the contact probability, that is probability that the filament is actually touching the barrier. And in fact, that is quite easy to calculate. Pi, if Pi is the probability to find the filament at a distance I from the binding site, you can actually write down master equation for Pi and solve them in steady state recursively. And I equals to 0 corresponds to the contact probability. And it's very easy to show that it is actually 1 minus the ratio between the depolymerization rate and polymerization rate for free filaments. So this is the velocity due to global movement. And to calculate the velocity due to local movement, we need to actually know at what rates these hills and valleys are flipping and what velocity is it contributing to the surface. And for this, I simplify the model further. First of all, notice that at the binding site, the transition rates are different from the rest of the system. So what we do here, we forget about the filaments altogether. We just consider a KPZ surface and we treat the binding site as the defect site. And then we can solve this problem, and we can actually calculate the rho, that is, we can actually calculate the average height profile for the surface, and also probability to find a valley and a hill at a particular distance I from the defect site. And then we can use it and calculate the final velocity. And as you see here, it matches quite well with our numerics, particularly for large L. Okay. Now, next is the effect of faster and slower barrier dynamics. So here, notice that there are two processes. One is the filament dynamics, and another is the dynamics of the surface. And so far, we were considering the case when both the time scales are equal. But suppose now we introduce some relative time scale, then what happens? So this is what we find. So we find that as we make the surface dynamics faster and faster, the force velocity curve shows this upward shift. So the qualitative shape of the curve can be tuned by changing the relative time scale between the two processes. And here we show the stall force decreases as the surface fluctuations become faster. In fact, this process can be, these trends can be understood by considering the fact that when surface fluctuations are faster, then the contribution towards to the velocity coming from the local fluctuations become more important. As a result, even for small or intermediate force, it is no more dominated by global movement alone, therefore it deviates from this exponential behavior. And moreover, if you, I'm sorry. No, it's so if you so another thing is this phenomena of stalling can also alternatively be interpreted as a balance between the global and local movement. So when local movements become more and more important, the balance is reached at a smaller force, and this is why the stall force goes down with increasing when the surface barrier dynamics becomes faster. Finally, another thing is how the shape of the barrier gets affected in this process. So here we find that as the load increases, then height profile of the barrier shows larger variation across the system. So we characterize it by considering 2 points, calculate the height difference between them, and find out how that difference is scaling with the separation. That exponent is known as roughness exponent, and we find that roughness exponent shows a continuous dependence on the applied force. And this sharp change happens at the stalling force actually. Finally, we can generalize these results to the case of multiple filaments. And here we find these are our results. Both our analytical calculations can also be extended in this case. And in this case, we find that the stall force is independent of barrier size, but it is proportional to the number of filaments. And in this case also, when we introduce a relative time scale between the two processes, then we find qualitatively the same effect. So in conclusion, I would like to say that we find a rich interplay between polymerization dynamics and membrane fluctuations. And this one important result is introducing a relative time scale between the two processes. The force velocity curve has a shape change. I would just like to mention something similar has been reported some few years back in this work, where a much more complicated model, a mesoscopic hybrid model was considered, where the actin filaments was modeled by semi-flexible polymers, and in addition, the active network was modeled like a macroscopic gel. And here it was found that depending on how fast the gel recoils, the force velocity curve can actually change from a convex to concave. And we also find that the shape of the barrier depends on the size of the load. So with that, I would like to thank you for your attention and wait for questions.
Thank you. We have time for 2 quick questions. Yeah.
Yeah, because because stall force, we are defining it as the velocity, force at which the velocity becomes zero. The local fluctuations of the surface actually changes the velocity of the barrier. That is why. Not only the time scale, I mean, even when you fix the time scale, even then you find that there is a dependence on the size of the barrier. It is coming because the local fluctuations actually, and how many, for a single filament, how many local fluctuations are taking place, that would actually depend on how many such free sites are there which are able to fluctuate.
Yeah, one quick question here.
If delta, then this 1 minus delta.
No, we have not used, exactly, load sharing we have not used, right.
So my curiosity was that membrane effect is producing something like a modification of the arrangement barrier with an effective delta curve. Because there change the delta curve.
Yeah. Yeah, so notice one thing though, that although we consider the fluctuating membrane where it is possible to do both global and locally distort it, but if you actually look at the probabilities measured from simulation, we find that this local valley to hill flip and then polymerizing, that process does not happen very often. Because actually most of the time at the binding site, the configuration is such that if you want to polymerize right at that point, you have to really push it. So it is not because, but the dependence is mainly, I would say, coming from the local fluctuations of the surface away from the binding site.